This notebook, we're going to continue exploring the use of files and file objects. And in this case, we are going to look at reading files over the web and reading files with standard formats. So to start with, we're going to look at reading files over the web directly with Python instead of using a third party like Pandas, which we have done in prior notebooks. And in this, if you are working in Python 2 instead of Python 3, there's been a big reorganization of the web library. And so what I'm demonstrating is in Python 3, and you'll have to look up the documentation of how to, essentially where the files are located in Python 2. So the first thing we're going to do is we are going to read in the python.org webpage. And we're going to do this with the url.request library. And this contains a function URL open, which is going to create a file-like object similar to what we have done when we do an open command. And then we're going to read in the content of the file, the web page, and we need to decode it. And so the decoding, the standard Unicode encoding is UTF-8 for English websites. And then we're going to use some of the special functionality of IPython to render that HTML page into our notebook. So the key feature here is really this import urllib.request. That's where the functionality for interacting across the web is located. And so we do this with urllib.request.url open. We give it the URL that we want to read from, and we create this file object response, and then we read, decode, and this gets assigned to this variable Python text. Python text this will contain the HTML that's defined on www.python.org, and then we're going to do the display here. So let's run this, and there's a lot that we're missing from the website. So if we just go to python.org, see we're missing all the file formatting, because that's all defined in separate CSS files. But if we scroll through here, we're going to see that we basically have the content of what was on that web page pulled into a string in our notebook that then we can manipulate, extract text from, etc. So that's a lot of information on that web page. Keep scrolling down. Okay, now instead of just reading, basically just pulling in the HTML from a web page, we're going to read a tab delimited file across the web. In this case, we're going to read a tab delimited file. It's on GitHub that has a knowledge base for my PyContext NLP application. And this is going to be similar. We're going to use the urllib.request.url open to create a file-like object, which in this case I'm going to call F0. And what I'm going to do here, though, is a little more complex. I'm going to read in the content of that file, decode it, and I'm going to use the default decoding, which is going to be UTF-8. But then I'm going to pass it to this string IO, which I import from IO. What this is going to do is it's going to take my string of data that I've read in, and it's going to convert it into a file-like object. So then I can pass this file-like object to the CSV reader. The CSV reader can then go through line by line. We tell it that the values are delimited by a tab, and we will then get a tab delimited list of data. Oops. So I skipped a line here somewhere in my imports. Or I did something wrong. So let me just add that import here. Okay, so this was read from this location right here, which let's just copy this, we did here. And this is the file that's located on GitHub. Tab delimited, lexical categories, regular expressions, and that is now available for us to work with inside our program, or in this case, our notebook. Okay, there's a couple other tools that will be really useful. One is the gzip library. So this will allow me to open a compressed file as if it were a normal file. So I don't need to think about first uncompressing a file, reading the content from it, etc. When I use gzip, it will automatically open and decompress the contents, and then I can read it in. And then we're going to demonstrate some serialization. Serialization basically refers to taking something in some object in our program and writing it out to disk for data permanence. So Pickle is a Python-specific format that allows us to write out arbitrary Python structures, including our own user-defined classes, etc. So it's very convenient for using if we are sticking within a Python environment. It has some drawbacks in terms of security, and that it is Python specific, so you can't use this to share data with like a R program or a Java program. Another serialization option for us is JSON, which stands for JavaScript Object Notation. And this is a common data exchange format. It's becoming probably the most common data exchange format on the web. It's more limited in what it can be serialized. There are like dictionaries, lists, tuples, integers, floats that are kind of these standard data types in Python are mapped to standard data types in JSON, but arbitrary data structures that we can create in Python aren't going to map directly to JSON. And so basically we either dump something out or we load something in. And so we'll go through demonstrations of this here. So in this case, I am going to I'm going to use the gzip library to open a file, demo.pickle.gz. So gz is the standard suffix for a gzip compression. And I'm going to write it out as a binary file. And so my file object is going to be fo. And if I create, in this case, I'm going to dump out data, which is what I've loaded in up here from my reading from GitHub for the PyContext knowledge base. And so I'm going to dump out that list of lexical concepts, and then I'm also just going to create this dictionary right here and dump this all out. And having done that, I can now read this back in. So in this case, I'm going to use gzip open, and I'm going to open it in a read mode. And again, the gzip is going to do the decompression for me. And then I just do load. I happen to know here that I had dumped out two data objects, and so I'm just going to do tuple unpacking here. So I'm going to have data1 and dict1, and I can print these data out that I read. So the first thing I have is my dictionary, which has a key of B and a value of 2 and a key of A and a value of 1, matching what I did up here. And now I have also that list of the PyContext NLP lexical terms. Okay, with JSON I can do something similar. In this case I'm not going to do compression, so I'm just going to open a file JSON demo, open it to write, and I'm going to dump out to that my dictionary that I defined and my data. And I can show you what this looks like. The JSON format is a textual format, so I can just read this in as a string. Or if I want to load it in, I can then load it into my particular data types. Okay, now if we move on to reading and writing images, there are a variety of options available for us to do this in Python. Kind of the The old standard was a library called PIL, Python Imaging Library. It's now been forked into a more, probably better licensing, more up-to-date module called Pillow. And we can install it with pip. It's already installed on our program in our environment. Simple ITK is a package that I use a lot that's designed for n-dimensional images, like a three-dimensional image like an MRI or a CT scan. It's a big package. It has a lot of tools for doing image segmentation, image registration, etc. in this, again, this multi-dimensional setting. SciPy is a package that has a lot of scientific programming tools, including tools for doing some image analysis and reading and writing images such as JPEGs and TIFFs. And a newer package is scikit-image, which includes a lot of tools for standard computer vision image processing applications. Finally, in this section, EXIF. So EXIF is an image format that the JPEG and the TIFF images follow, and it defines what the header of an image looks like. And the header is what contains the metadata, the data about the data, that's important for interpreting the content of an image. And so I'll demonstrate some of these here. So in this first cell, I've just got a PNG file sitting in a data directory on our system, and I'm going to use the SciPy function's image read to read this image in. I can do some resizing of it. So in this case, I'm going to read in my image. I'm going to convert it to a quarter of its original size, and then I'm going to use matplotlib to display the image in the notebook. Except I keep forgetting to evaluate these cells. All right, let me come back down here. So there's a false color rendering of a maximum intensity coronal, actually sagittal image of a CT of the head and neck of a patient. Okay, I can do the same thing with scikit-image. It has its own I/O package. In this case, I'm going to read it in and display it with the scikit-image functions. And we can also use scikit-image to save out an image. And in this case, I'm just going to save it out in a different format, in a PNG format. And if I do a list of what my directory content is, I now have this dog.2 PNG file that I created. Now you notice that the dog.2 PNG file is substantially larger than the dog.jpg, and that's because the JPEG has compression and the PNG file does not have compression in it. Okay, so to look at the header of a JPEG or TIFF image, we need the EXIF read library, which we can install with pip. And now if we read in the JPEG image, this is the header or the metadata about the image. So it tells us what the color space we're using, the sRGB. It'll have when the image was acquired, what the camera settings that I was using were. If I'm using a camera with that has a GPS in it, it'll give me the coordinates of where the photograph was taken, what the white balance is, etc. Another data type that we might run across in biomedical applications are audio files. And SciPy has functionality for reading in WAV files, which is one common format for audio data. And the metadata here is quite simple. When we read in the image, we're going to get two pieces. We're going to have a rate, which is the sampling rate in hertz, and then we're going to have the data, which is the actual sound wave, which is a NumPy array of the time series. So we read that in, and then we can play this out on our computers. course, if we mess with the rate, our audio is going to have a different sound. So in this case, the metadata associated with our data is this rate, or the telling us what frequency the data were sampled at. And that's what our original time series looks like. The final format I wanted to display here is DICOM. DICOM is the standard image format for medical imaging within radiology. Pathology has now largely adopted it, and there are DICOM standards for including in data from other imaging specialties like dentistry, dermatology, ophthalmology, etc. And so we're going to use a DICOM package called PyDICOM, which we import as DICOM. And again, on our data directory, I have some CT images, and so here we're going to read in a CT image of the chest. And when we print the object that we read in, we see the header. So the DICOM header contains the information that is specific to describing this DICOM image. And so there's a lot of information about when it was created in terms of date and time, who the referring physician was. These have been de-identified, so that none of that information is here. And then specific patient's name, ID, birth date, sex, age, etc. And then information about what were the physical parameters of the in this case, CT scanner that were used to acquire this image. So this is important information for making meaning out of the pixels that the image is generated from. And then we can look at the contents of that image here, and we see this axial slice through the chest at the level of the heart.